In this lesson, we're going to explore and apply several properties of logarithms. Let's take a look at some familiar logarithms. So, in order to set this up, we need to find log base 2 of 8 times 4. Well, order of operations tells us to do the inside of the parentheses first. So this is going to simplify to log base 2 of 32. Now remember that when we're finding a log, you're finding the exponent to which 2 should be raised in order to get a result of 32. And since 2 to the 5th is equal to 32, the log base 2 of 32 is 5. Below, let's take a look at the log base 2 of 2 times 32. 2 times 32 is 64, and 64 is 2 times 32, so that would require an exponent of 6 to get there. Then some lower value logarithms. Log base 2 of 8 is 3, since 2 raised to the third power is 8. Log base 2 of 2 is 1, since a 1 exponent is required on a 2 to get a result of 2. And log base 2 of 4, the exponent required there is 2. We can square 2 to get 4. And I think we talked about log base 2 of 32 is 5. All right, so now let's take those values and let's insert them here in each of these statements. So log base 2 of 8 times 4 is, we said that's 5. So 5 equals log base 2 of 8, which is 3, and log base 2 of 4, which is 2. I think we can argue that there should be a plus sign there. 5 is equal to 3 plus 2. All right, let's take a look at the second group of related logarithms. Log base 2 of 2 times 32 is equal to 6, so 6 equals log base 2 of 2 is 1, and log base 2 of 32 is 5. Again, I think we can argue that there should be a plus there. And there's a reason for this. When we multiply like bases, for instance, 8 times 4, 8 times 4 is 2 raised to the third times 2 raised to the 2. And when we multiply those like bases together, we simply add the exponents. And as you well know, a logarithm equals an exponent. All right, let's take a look at a similar type of situation, but with division this time instead of multiplication. Log base 2 of 8 over 4, or 8 divided by 4, is the same as log base 2 of 2, which is 1. Log base 2 of 2 32nds. If we reduce that fraction, 2 32nds is 1/16. And so now we're looking for that exponent that I can put on a 2 to get a result of 1/16. And 2 raised to the negative 4th power is 1/16. Some familiar logs that we've looked at already. Log base 2 of 8 is 3. Log base 2 of 2 is 1. Log base 2 of 4 is 2. And log base 2 of 32 is 5. So let's put those in each of these statements. Log base 2 of 8 divided by 4 is 1. Log base 2 of 8 is 3. And log base 2 of 4 is 2. And I think we can argue that there should be a minus sign there. And log base 2 of 2 32nds has a value of negative 4. Log base 2 of 2 is equal to 1. Log base 2 of 32 is equal to 5, and 1 minus 5 is equal to negative 4. This is really similar to the other property that we just looked at with multiplication. Of course, when you're dividing, you simply subtract the exponents, so we're just subtracting the logs. So let's generalize these properties now. The log base b of m times n is equal to the log base b of m plus the log base b of n. And similarly, the log base b of m divided by n is the log base b of m minus the log base b of n. All right, let's take a look at another property now. Log of 100 raised to the 4th power. Well, 100 raised to the 4th power is 100 times 100 times 100 times 100. And of course this is a common log base 10, so if we want to count the number of zeros there, this will give us the value of the log, the number of times that 10 has been multiplied together. And there are 8 zeros there, so this has a value of 8. Log base 10 of 100 cubed. So 100 cubed is equal to 100 times 100 times 100. And so now we have a total of 6 zeros there, so the value of the exponent on 10 must be 6. In other words, 10 to the 6th is equal to the 1 million that we got inside the parentheses. And log of 100 is 2, because 10 squared is 2. All right, let's put those in some statements that relate these logs together. The log base 10 of 100 raised to the 4th power was 8, and the log base 10 of 100 is 2. So I think we can argue that we need times 4 there. And the log base 10 of 100 cubed is 6. Log of 100 is 2, so we need a times 3 there. This brings us to what's called the power property. And the power property states that if you have the log base b of m raised to the k power, that is equal to k times the log base b of m. In other words, whatever exponent was raising the argument of the logarithm, that exponent can be moved outside of the log and multiplies the value of the log without the exponent. All right, so let's use those properties to do what we're going to call expanding a logarithmic expression. What we're going to do here is write this in terms of log of x, log of y, and log of z. So right now we have log of a much more complicated expression. So what we can first do is, since this is 3 things that are being multiplied together, is we can write these logs separately. That is to say, using the product property, this is log of x squared plus log of y cubed plus log of the square root of z. And of course, what we want to do here is write the square root of z as z raised to a power, and the square root is equivalent to power of 1/2. The next thing that we can do to get this in terms of just plain old log of x, log of y, and log of z is to use the power property. Log of x squared is 2 times the log of x. Log of y cubed is 3 times the log of y. And the log of z to the 1/2 is 1/2 times the log of z. So now that's a fully expanded expression, and we have it in terms of log of x, log of y, and log of z. All right, let's take a look at another. Log base 2 of 32 over xy cubed. So here we have a division. So we can write this as log base 2 of the numerator minus log base 2 of the denominator. The log base 2 of 32 can be simplified. That's just 5. And then the log base 2 of xy to the 3rd power is equivalent to the log of x plus the log of y cubed. Now I have to use parentheses because everything that the log that follows the minus sign here is equivalent to must all be subtracted. So we're going to have to distribute that minus sign to both of those terms inside the parentheses. So we've got 5 minus log of x minus log of y cubed. And lastly, we can fly down that exponent on the y so that we have this just in terms of log of plain old y. So again, our final answer is in terms of just a log of x and a log of y. All right, there are a couple for you to try. So, oh, actually, never mind. We're going on to example 2. And we're just going to do this in reverse here. We're going to write this as one single logarithm. So we're going to do everything that we did in reverse here. So you can think of it in this way. We need to take care of our multiplications. 5 times the log of x is the log of x to the 5th, plus, and 2 times the log of y is the log of y squared. So we've taken care of our multiplications first before we take care of that addition and subtraction. And then 3, in order to express this inside of a logarithm, we have to write it as the log of a number here. And if the log is equivalent to 3, that means the exponent is 3. Now remember, our base is 10 because this is a common log. So 10 to the 3rd power is 1,000. So log of 1,000 is equivalent to 3. And now we can use our product property. This is log of x to the 5th times y squared. And lastly, use the quotient property to take care of that subtraction. Log of x to the 5th y squared over 1,000. And now we have this written as a single logarithm. Let's try one more. 2 minus log base 3 of x plus log base 3 of y. So again, we have a single number sitting here, 2. This needs to be expressed as a logarithm. So this is the log base 3 of 9, since 3 raised to the 2 power is 9, minus the log base 3 of x plus the log base 3 of y. So with addition and subtraction, we have to take care of the operation that's on the left first. So we don't want to do that addition first. We need to do the subtraction because it's on the left. So doing the subtraction, that's the log base 3 of 9 over x plus the log base 3 of y. Now when we add the logs, we multiply their arguments together. And so we're thinking the next step is going to involve 9 over x times y. And of course, if you multiply 9 over x times y, the y multiplies into the numerator. So the final result here is log base 3 of 9y over x. Now I want you to notice something about this final result. What we can notice is the logs that had a positive coefficient, log of 9 and log of y, their arguments wound up in the numerator of the final answer. And then the logs that had a negative coefficient, the x, that x argument wound up in the denominator of the argument of the single log. All right, let's move on. Now we're going to use some properties of logarithms here to simplify some of these expressions. Log base 3 of 9 raised to the 13th. Well, no one wants to raise 9 to the 13th power. But what we can do here is we can simply use the power property to rewrite this as 13 times the log base 3 of 9. And the log base 3 of 9 is 2. So that gives us a final result of 26. In B, we have a logarithm that can be condensed into one single expression. We can probably do this all at once in one step here. Log base 3. Oh, by the way, these should all be log base 3. Sorry about the typo there. This should be log base 3 of, and everything that has a positive coefficient is going to wind up in the numerator of the argument of the single log, and everything that has a negative coefficient is going to wind up in the denominator of the single log. So now let's simplify what's inside the log. 0.18 times 100 is 18, and then divided by 2 gives us the log base 3 of 9. That's equal to 2. Let's try 1/2 times log base 7 of 16 minus log base 7 of 28. we have to take care of that multiplication first and rewrite this as 16 to the 1/2. 16 to the 1/2 power is the square root of 16. So this is log base 7 of 4 minus log base 7 of 28. Now subtracting those logs, we're going to simply divide their arguments to write it as a single log. And 4/28 is the same as 1/7. And the log base 7 of 1/7 is the exponent -1 that's required to raise 7 to a power to get 1/7. One more here. Again, we're going to use the power property first to take care of our multiplications. So 2/3 times log base 6 of 8 is log base 6 of 8 raised to the 2/3. And the next term is going to be log base 6 of 3 squared. Remember, an exponent of 2/3 means the denominator gives us the number of the root, so that's a third root or a cube root. And the numerator gives us the power, so the third root of 8 is 2, and 2 squared is 4. And then 3 squared is 9. When we add those two logs together, we're going to multiply their arguments, and 4 times 9 is 36. And log base 6 of 36 is the exponent 2. All right, these are kind of fun here. We're going to use the fact that you have a couple of log values that are given to you. We're going to use those values to estimate the logarithm of some different values. So log base a of 2/9 can be re-expressed as log base a of 2 minus log base a of 9. And we just so happen to have those values. Log base a of 2 is 0.69. Log base a of 9 is 2.20. And if we subtract those, we get 1.51. Log base a of 18 can be re-expressed as log base a of 2 times 9. So that'll be log base a of 2 plus log base a of 9. Log base a of 2 is 0.69, and log base a of 9 is 2.20. Adding those together, we get 2.89. For C, the log base a of 8 can be re-expressed as the log base a of 2 raised to the 3rd power. Now we can use the power property and bring that 3 down as a coefficient. So it'll be 3 times the log base a of 2, or 3 times 0.69, which is 2.07. In D, we have the log base a of 3. Now 3 is a little bit more tricky. What you have to realize there is that is 9 raised to the 1/2 power, or the square root of 9. So we can use the power property here as well. And then log base a of 9 was 2.20. Multiplying those two together, we've got 1.10. Log base a of 36 is log base a of 2 squared times 9. If you expand that, you're going to get log base a of 2 squared, and you can bring that exponent down in front. So that'll be 2 times log base a of 2 plus the log base a of 9. So it's 2 times 0.69 plus 2.20. 1.38 plus 2.20 is 4.58. And the last one, log base a of 1/2. This is the log base a of 2 raised to the -1 power. So this will be -1 times the log base a of 2, or -1 times 0.69, -0.69. All right, now let's take a look at one more property of logarithms. that one more property is the change of base formula. So we're going to attempt here to change the base of log base 7 of x to log base 3. So for the first step here, we're going to take this equation y equals log base 7 of x and rewrite it in exponential form. So in exponential form, it'll be 7 to the y is equal to x. Now we're going to take a log base 3 of both sides of the equation. So log base 3 of 7 raised to the y equals the log base 3 of x, and use the power property on the left side. So now we have y times the log base 3 of 7 equals the log base 3 of x, and finally divide to solve for y. So y is the log base 3 of x over the log base 3 of 7. So what I want you to notice here is we took an original expression here. So our original expression was log base 7 of x, and we solved for y, which is equal to that, and just re-expressed it in a different form. That's equivalent to log base 3 of x over log base 3 of 7. Now we could have converted to any other base here. So the 3 was just an arbitrary number that was chosen here, just to illustrate the property. But in general, the change of base formula says that the log base b of x is the log base a of x over the log base a of the original base b. So we've changed the log base b of x into base a by dividing the log base a by the log base a of the original base. Now, a is just an arbitrary number. This could be base 10. So this would be log base 10 of x over log base 10 of b. It could be natural logs, natural log of x over natural log of b. Doesn't really matter what base you choose. The reason why change of base is used in general is to change to a more convenient base. For instance, calculators for many years did not do bases other than 10 or e. So it was necessary, if you wanted to use that for a calculation, to change your base in order to put it into the calculator. All right, now below what you'll see is a list of all of the properties that we have studied in this unit so far. We have logarithmic to exponential in number 1. Number 2 just states what's the domain of a logarithmic function. Its argument is a positive number. In 3, we have the log of 1 is equal to the exponent 0, and the log base b of the base itself is equal to 1. 5 and 6 are the inverse properties, and then 7, 8, 9, and 10 are the 4 properties that we've developed during this lesson. Now we can use those properties to re-express certain expressions. Use the power property to rewrite the log base 5 of 32 over the log base 5 of 8. Since I can't calculate the log base 5 of either of those numbers without a calculator, what we can do is rewrite the log base 5 of 32 as the log base 5 of 2 raised to the 5th power. Downstairs, that's the log base 5 of 2 raised to the 3rd power. Now we can use the power property to rewrite this as 5 times the log base 5 of 2 over 3 times the log base 5 of 2, and then cancel our common factors of log base 5 of 2. So our final result is 5/3. In B, we're asked to just use the change of base formula. Well, remember the change of base formula states that the log base b of x is equal to the log base a of x over the log base a of the original base. So what you'll see is an expression here that looks a lot like the right side of that change of base formula. So what we can do is rewrite that as the log base 8 of 32. Right, because the base is on the bottom in that fraction. All right, well now when we write the log base 8 of 32, our thought has to be that we are looking for that exponent that I can put on an 8 in order to get a result of 32. Well, this can be solved by expressing these as common bases. So 8 is 2 cubed raised to the x equals, and 32 is 2 to the 5th. When you raise a power to a power, you multiply those exponents. And now we can simply equate the exponents. So 3x is equal to 5, and x is equal to 5/3. So the log base 8 of 32 is 5/3, and that's the same answer that we got when we used the other properties. So you have several different techniques that you can use. All right, let's now put all of our properties together and see what we can do to re-express some more complicated expressions. Log base 8 of 49, I don't have any idea what that number is. I could estimate it for sure, but we can't compute it exactly without a calculator or a table. Log base 7 of 1/2, similar story. But what we can do is we can use the change of base formula. You'll notice they're different bases. Now when we change the base, the question is always, what do I change the base to? And the answer is it doesn't matter. I'm going to change these to common logs. That way I don't have to write the base. So this would be, log base 8 of 49 would be the log base 10 of 49 over the log base 10 of the original base. Log base 7 of 1/2 would be the log base, we're multiplying these, this would be the log base 10 of 1/2 over the log base 10 of the original base 7. Now we can use power property. Log base 10 of 49 is log base 10 of 7 squared. Log base 10 of 8 is log base 10 of 2 cubed. The log of 1/2 is the log of 2 raised to the -1. And the log of 7, I don't think we're going to be able to do anything with that because 7 is a prime factor. Now let's just use the power property and fly those exponents down. 2 times the log base 10 of 7 over 3 times the log base 10 of 2 times -1 times the log base 10 of 2 over the log base 10 of 7. Now you can grab your handy dandy cancellation pen, cancel those log 7s, and cancel those log 2s. And that gives us just 2/3 times -1 is -2/3. Let's take a look at this next one. We've got 3 logs to multiply together, and again, it doesn't matter what you change the base to. This time, just for grins, I'll change it to a natural log, so a base e. That means I only have to write 2 letters. So changing this to a natural log of 9 over natural log of 2 times natural log of 8 over natural log of 5 times natural log of 25 over the natural log of 3. Now let's re-express these. 9 is 3 squared. 2 is a prime factor. 8 is 2 cubed. 5 is a prime factor. And 25 is 5 squared. And 3 is a prime factor. Now we can fly those exponents down or use the power property. We have 2 times the natural log of 3 over the natural log of 2 times 3 times the natural log of 2 over the natural log of 5 times 2 times the natural log of 5 over the natural log of 3. Now we're going to have some logs to cancel. Natural log of 3, natural log of 2, and natural log of 5. That leaves us with 2 times 3 times 2 is 12. And for this next one, we need to take care of the addition on the inside of this parentheses first before we multiply. And when we add logs, we multiply their bases, or their arguments, excuse me. So they're both base 27, so we can multiply them together and get the log base 27 of 32 times 1/4, which would be 8. And then we're multiplying that by log base 2 of 9. Again, we can change to whatever base we want to. I'm just going to change to natural log here. So this is natural log of 8 over the natural log of the base. Remember the base in change of base formula, its log always goes on the bottom of the fraction. And then log base 2 of 9 would be natural log of 9 over natural log of 2. 8 is 2 cubed. 27 is 3 cubed. 9 is 3 squared. And 2 is a prime factor. So now let's use the power property. 3 natural log of 2 over 3 times the natural log of 3 times 2 times the natural log of 3 over the natural log of 2. We can do some canceling of common factors. Natural logs of 2 and natural logs of 3. And both of those 3's, that just leaves us with a final result of 2. All right, just one more. This one is interesting because it has 1 over a logarithm. Now again, we can use the change of base formula here. If we change log base 2 of 4 using the change of base formula, that would be natural log of 4 over natural log of 2. So what happens if we use the change of base formula on 1 over that expression? That's just going to simply be the reciprocal of what we just wrote above. So natural log of 2 over natural log of 4. And the log base 8 of 4 is the natural log of 4 over the natural log of 8. So 1 over it will be the natural log of 8 over the natural log of 4. Now, nicely for us, we have a common denominator. And when we add fractions that already have a common denominator, we just add their numerators and keep the denominator. Natural log of 2 plus natural log of 8. When we add logs, you can multiply the arguments together. 2 times 8 is 16. And then we can use our power property on this. If we want to, we can write 16 as 4 squared, and that will be 2 times the natural log of 4 when we fly down that exponent. And we can simply cancel those common factors of ln 4. That means that this result is 2. Now, I do know that we could have computed the log base 2 of 4 and the log base 8 of 4 in the original expression, but this is another interesting way to do it. And of course, if we have logs where we're not able to compute the values very easily, this can provide us with another way to approach that. Well, that's it for the lesson.